Hello, today's topic is moment generating function. For each random variable capital X, we can define its moment generating function by mxt, which is defined as expectation of e to the power tx, like this. For discrete case, it can be written as e to the power txi probability of xi, where probability of xi is the PMF, where x is discrete. And for continuous case, it can be written as minus infinity to infinity e to the power tx fx dx, where x is continuous. Okay. Mxt is called the moment generating function because we can find all the moment of x by differentiating mt and then evaluating at t equals to 0. That is, first of all, we do the derivative on the moment generating function, that is ddt of expectation of e to the power tx, which is nothing but expectation of d dt e to the power tx, and it can be written as expectation of x e to the power tx. Okay. Now evaluate at t equals to 0. Let me take another color. Now evaluate at t equals to 0. Therefore we get m prime 0 as expectation of x e to the power 0, which is nothing but expectation of x. And similarly, if we do the double derivative on mxt, then we get d dt of expectation of x e to the power tx, which results in expectation of x square e to the power tx. After putting t equals to 0, we get m double prime t is equals to expectation of x square. So in general, we can say that for all n is greater than equals to 0, we have expectation of x to the power n is equals to mn0. Therefore, for all n greater than equals to 0, we have expectation of x to the power n is mn0, where mn means the nth order derivative taking t equals to 0. Okay, so these are the different order of raw moments. Now let us check this concept with an example. Okay, first we check the moment generating function for a Bernoulli distribution. Now we know that the Bernoulli probability is defined as P and the failure probability is defined as 1 minus P. Therefore, mxt is equals to expectation of e to the power tx, which is nothing but e to the power t0 into probability 0 plus e to the power t into 1 probability 1. And it is nothing but, as we know that e to the power 0 is 1 and p0 is 1 minus p, and it is going to be to the power t So this is the moment generating function of a Bernoulli distribution. Now we check the moment generating function of a normal distribution. Okay. For normal distribution, if x follows a normal distribution mu comma sigma square, then expectation of e to the power tx is going to be integration e to the power tx fx dx. Okay. As we know that we can write it as expectation of e to the power t mu e to the power t sigma z, where z is a standard normal variate. Here e to the power t mu is a constant, and we can write e to the power t sigma into z like this. Okay, so this is going to be mx t sigma, and e to the power t mu, and this is mx t sigma. Okay, and it can be written as e to the power t sigma square divided by 2. So therefore the moment generating function is going to be mu t plus t square sigma square divided by 2. Here the mx t sigma is the MGF of standard normal variable. Standard normal variable. And we already know that the MGF of a standard normal variable is e to the power t sigma square divided by 2 if the parameter is t sigma. And after multiplying these two things, that is e to the power t mu and e to the power t sigma whole square divided by 2, we get e to the power mu t plus t square sigma square divided by 2. So this is the MGF of a normal variable. So that's all for today. Thank you very much.